So we are introducing our second panel this afternoon about innovation at the service of circular economy, transforming waste into resources. And we have Álvaro Silva. He's the project manager of factory and resource recovery of Cetaqua. Then we have Miguel Mauricio from the University of Santiago de Compostela. And finally, Antón Taboada, who is the project manager of Cetaqua. So welcome to this panel, and we are going to start with our first panelist, Álvaro Silva. You have the floor. Biofactory and waste recovery at Ecoval Sudoe. Thank you very much, Álvaro. Whenever you're ready, you have the floor.
Thank you very much. I hope that you can all hear me all right. Okay, please let me know whether I'm sharing my screen, so that you can all see my screen. Okay, so there I go. First off, I would like to extend my appreciation to FEUGA for allowing us to take part of this webinar to walk you through the cornerstone of Cetaqua that belongs to the AWAR group. This is a center that is located in Galicia. First of all, we should say that in Galicia, we are focused on reclaiming resources from waste. That is to say, our core activity is about actually making history of waste so that it becomes a historical development rather than a present development as it currently happens. As you know, waste is a fraction of a whole or a material that is no longer used after some kind of activity has been performed. This should be part of the past, so we have to make our small contribution in order to make this circular and in order to come up with resources. That is something that is useful in order to meet a need or a good or service that is required in order to carry out something in particular or make something become real. So we want to do this. We want to turn waste into resources for different purposes. At Cetaqua, coming from AWAR, we were historically tied to the comprehensive cycle of water treatment. In Santiago de Compostela, the AWAR Center treats water from a comprehensive perspective, so that is our core business. These are the wastewater treatment plants. Little by little, we are moving towards the industrial sector, also placing an emphasis on wastewater facilities. We are also trying to work on reclaiming water, stepping outside of the biological systems that normally prevail in water treatment and cleaning. So we do our best in order to use reclaimed water, that is to say water coming from households is cleaned, and then additional properties are put in order to use them for garden watering, for irrigation purposes, and also for street cleaning. We also do our best so that all the water coming from households can be caught in order to produce green energy by using some or by running some biological processes. So carbon can be turned into an energy generating gas. We also try to catch resources from solid urban waste. Martin from COVAX before spoke about this already. we are used to working in wastewater treatment plants that are mainly located in urban areas. Today, in Santiago or in any other Spanish city, normally we transport water from cities or from a certain source to cities. We spend a lot of money to treat that water, and then we bring that water back into to its natural source. When modern facilities exist, created after 2020, we can reclaim water quite effectively and efficiently. In this case, all the waste coming from these wastewater plants, that is to say the sludge, is subjected to an anaerobic process in order to obtain biogas, which is a source of energy that can be used either to produce electricity in the wastewater plant in itself, or else it can be subjected to other processes in order to use it for other purposes. So this is the current scenario, but we are working in order to build a different scenario in the future. That's what technology centers are now doing. So some of these technologies already exist, or they are quite advanced in terms of development. So we want to leave the model that you see on top behind. This is a linear model that is different from the one that you see at the bottom, which is a circular model. In this case, we want to turn these plants into biofactories. In the past, resources could not be produced unless poor quality water was used. Now we're going to use or produce water by using urban solid waste, among others. So as I said before, the carbon contained in organic matter and wastewater, both coming from households, for example, carbon coming from food scraps or wastewater, these all come from households, and this is what happens before they go back to their natural sources. Carbon can be transformed into energy in different ways, for example, through by transforming sludges, and in the future we will try to turn this carbon into volatile fatty acids. We will see how we are going to do that, and now let me tie this part of the presentation to the following one. The ultimate goal here is to produce a different kind of fuel. In addition to carbon, we will also take into account nutrients that are found in wastewater. We will explore new ways of reclaiming phosphorus, for example, in order to produce fertilizers that requires low application. That way we can use these fertilizers little by little in such a way that soil can better absorb all the fertilizer load without contaminating water layers, as it happens today with the application of traditional fertilizers. As you can see here, there's a lot of theory behind reclaiming resources. There's a lot of scientific literature available on the matter. This is something that you can find in many databases. These are the different limits showing how far we can go. We know that we are not going to live forever, and therefore we need to make our small contribution by putting in place different initiatives in order to reclaim resources that today are considered to be waste. We can therefore keep them in the value chain, therefore reducing the exploitation of natural resources. For instance, in the case of grapes, as we heard before, there are some compounds called polyphenols The CIGAT Biofactory project is working on polyphenols by applying a separation physical process. We want to run an ultrasound process in order to obtain polyphenols that can be applied in different industries. For example, polyphenols can be used as a raw material in other industries, such as in the food industry, in the cosmetics sector, or in food and beverages at large. At a low quality level, in the case of high quality polyphenols that could be used for pharmaceutical purposes, but that will take longer. This is a process where the viticulture waste is subjected to this process, to some ultrasound process. We use a number of membranes in order to obtain different degrees of purity of polyphenols. We can then use these resources according to the end users identified for this purpose. Within the framework of the Conserval and the CIGAT Biofactory project, we will be able to obtain what we call volatile fatty acids, or VFAs. For example, we will be able to obtain acetic, propionic, and butyric compounds that today are found in the petroleum industry, even though they are similar to petroleum chemistry. We want them to come from waste sources after an anaerobic fermentation process. We want to obtain these acetic, propionic, and butyric compounds by using biotechniques. For example, in the case of the canning and the dairy sectors, we can apply a fermentation process followed by a separation process that we are not working on. We can also use biomembranes in order to obtain purity levels that can be as similar as possible to these compounds that today are found in the petroleum industry. The aim, therefore, is to have VFAs that can be marketed in other industries, for example, to produce bioplastics, polymers, and also oils and fuels. What are we doing at present? We are still at incipient stage. We are taking some baby steps. In the case of the canning and the dairy sector, we can turn VFAs up to 90% with different degrees of purity in each case. Now, if we move forward at a teenage stage, we are doing this at a 70%, and at pilot scale, we are transforming carbon at a rate of 50%, and we believe that this rate could be further increased. So we will be able to twofold the amount of carbon in the form of VFAs. Cetaqua is well acquainted with water-related processes because we have more than 150 years of experience in this area. We know that sludge contains many resources that are not being exploited. So we believe that right now this is not being managed, or it's actually being managed as waste, but VFAs are not being obtained. Therefore, we want to start using industrial wastewater, but using sludge coming from wastewater plants. We want to therefore create acetic, propionic, and butyric compounds. And we want to take one step further if possible. In addition to sludge, we are also trying to aim at organic fraction solid waste processing. In addition to sludge, we would also like to introduce OFSW in order to increase the volume of VFAs. And that way, other industries will be able to obtain bioplastics, oils, and other consumer goods by using these resources. We are also working on different experiments at a larger scale. We have also run some surveys and we have obtained satisfactory results. We intend to increase, therefore, the resulting volume of VFAs. In closing, just like some of my colleagues said before, all this experimental work is in line with the EU strategies, Madrid strategies, and the government of Galicia's strategy. Everything we are doing is intending to fostering the circular economy, but putting in place all the actions that are being promoted by Brussels, Madrid, and Santiago, always in accordance with the European Green Deal, and of course with an outlook on attaining the UN SDGs. And that's all. Thank you very much for your attention. And afterwards, I will be open to answer any questions during the debate. Thank you so much, Álvaro. Now we are going to move on with Miguel Mauricio from CRETUS, from the University of Santiago de Compostela. He will speak about technological development, application of mathematical models for the design and optimization of bioprocesses. So, good afternoon, Miguel, and thank you very much for being with us. Thank you for having me. I'm pleased to share this panel with all of my colleagues who have just done very interesting presentations. Okay, the focus of my presentation is concerned with the hindrances to designing processes. Álvaro, for example, referred to this in his presentation. So I will try to show how, by using mathematical models, we can design and implement bioprocesses with the aim of building a circular economy. So let's go straight to the point. Mathematical models can help us to run simulations. For example, if we have a biological transformation and if we know how it works, if we know the pH, the substrate nature and composition involved, and if we know the simulation models enable us to determine whether this is going to be a selective model, whether it's going to be productive or not, whether by applying this model we are going to increase our output or not. And we have other ways of using these models by design. Therefore, let's suppose that I want a high selection of a certain compound, for example, of butyric acids in a particular product. What kind of waste can I use to get there? Under which conditions should I work? So I know that this may sound kind of rocket science, so let me try to throw some light by giving you a concrete example. These are the VFA's biofactories that Álvaro also mentioned during his presentation. So this biorefinery or factory for VFAs is an interesting concept because it's highly versatile. It can be used with different kinds of waste with little separation. It's highly flexible. And this flexibility eventually lead to obtaining VFAs, for example, acetic acid, propionic, butenic acid, among others. And the second step is to turn those intermediate products, called platform-based products, into a whole range of products that could be very useful. All these are chemical products that can be turned into fuel generating products, for example. They can be used to produce bioplastics, electricity, among others. The University of Santiago de Compostela and in our center, we have been working for many years in designing processes for bioenergy. We are now working with Conserval and Ecoval. Álvaro also mentioned these projects before. So the first step in carboxylate refineries has to do with anaerobic fermentation in order to transform organic matter into these end products. So how can we apply mathematical models in order to obtain VFAs? The first step is about anaerobic fermentation that leads to VFAs, but sometimes it's very difficult to predict. It's going to be a mixture always, and it's difficult to see which compounds will prevail, if any. Besides, these prevailing compounds may vary to a great extent and not in an obvious manner according to the substrate and the operating conditions. We have worked to show that mathematical models can be key in predicting the products that could be eventually obtained with high selectivities in order to obtain products from recovered waste. For many years, we have been developing mathematical models at metabolic level in order to turn mainly carbohydrates or waste containing high levels of carbohydrates and proteins into VFAs. So this kind of waste eventually result in VFAs. These are the intermediate VFAs that we are interested in. So what are these mathematical models like? These models are concerned with a number of biological processes performed by certain microorganisms. So they describe a number of metabolic transformations inside the cells of these microorganisms. So this shows how the different substrates get into the cell. Glucose or energy is required, therefore this will have an impact on the metabolism of microorganisms through amino acids or proteins or carbohydrates. They come into the cell and eventually, after a number of chemical reactions, they result in these products, the propionic, butenic, and these kind of acids. So how can we predict the compounds that will prevail in these transformations? Well, we can apply a number of biological fundamentals. We know, for example, that in fermentation processes, these products are the ones that will allow cells to grow more or obtain the greatest amount of energy possible. As I said before, this can be depicted mathematically, and eventually it enables us to predict the main fermentation products. This chart, for example, shows on the horizontal axis at the bottom the gelatin concentration in the feed. Here we had two residual flows, one that is rich in proteins and another one rich in carbohydrates. 100% of the flow here would be rich in carbohydrates and the other one rich in proteins. If we change the proportion of both flows or streams and according to the pH under which fermentation is performed, we can obtain different areas with either one VFA prevailing or another. We can have butyric acid, for example, or else with a moderate or high pH, we can obtain other results. If, for example, we want more aseptic acids, we can start using other streams or flows using high levels of protein. So, of course, this can also be translated into more quantitative calculations. Within the framework of the Conserval project, we want to predict not only how VFAs are produced, but also how salinity in the wastewater of canning facilities will affect the production of VFAs. Therefore, we need to expand our mathematical models, taking into account the metabolic transformation carried out by microorganisms in their cells in order to face this salinity or saltine accumulation that sometimes can be tough on microorganisms. Here we have represented different behaviors, mathematically speaking. For example, there is an adaptation strategy that is called salt-in. This means introducing other types of salts, like for example potassium ions to compensate the sodium ions, or else the accumulation of compatible solutes to allow cells to withstand salinity better. How can we tell, or how do we identify the strategy being followed by each cell? Here we're trying to develop bioprocesses by applying mathematical models. So we will have to run experiments at the lab in order to validate all these models. We have some reagents used for fermentation, for example, for carbohydrates and proteins with different salt concentration levels, and that enable us under controlled conditions to learn which mechanisms are applied by microorganisms to see how they withstand salinity and how this affects our products or the products that we are seeking to obtain. So the salting strategy, for example, will not alter the VFAs that might result. That's quite interesting. However, the number may be lower at the end, or they may be produced more slowly. We also know that producing an ex novo compatible solute, these may be interesting compounds. For example, there are some products that can be used for cosmetic purposes. This, however, requires a high level of energy consumption by cells, and therefore this may lead to a reduced amount of VFAs. Therefore, if the cell is producing this compatible solute, this happens with gelatin, for example, we will have fermentation of this kind that is acetate, propionate, and butyrate to another one that will be less aseptic. So we can have intermediate situations as well. We are using compatible solutes that can also be substrates, so the change of spectrum here will be different. By bringing all the experiments together and running our models, we can do some predictions as to what is going to happen. And how do we use this to develop bioprocesses? As I mentioned before, we have simulation. We can screen the different wastes and the simulation conditions. We can try out different waste water material from treatment plants, or from, for example, organic matter from industrial facilities, or solid waste. Alternatively, by choosing a certain product and certain selection criteria, we can also decide how we can better mix different waste or residual sources, or whether we have to add a chemical compound that can act as a compatible solute so that microorganisms in canning water can withstand salinity. Perhaps we have to use some kind of product with a high content of visceral. So by developing these models, we can produce much more effective processes or contributing to the circular economy. This is another example. If we wanted to maximize value production in an SBR using wastewater containing a certain amount of casein, for example, water from a dairy producing plant, by changing the operation variables such as the pH or the solids withdrawal ratio or the cycle length, trying to produce valerate while avoiding producing methane. Well, according to the goal we pursue, here you can see the cycle length and the solids withdrawal ratio. If our goal is to maximize selectivity so that we can turn waste into VFAs mainly, we will have to work at short cycles, at short withdrawal ratios, and with a pH near 5, where we have the maximum selectivity possible. However, if we have a different productivity aim, we are going to also work at short solids withdrawal ratio, but this is kind of risky because one portion can turn into methane if we deviate too much. Productivity, however, in this case would be higher in order to obtain this particular fatty acid. This is just a biological model with some inherent error. All the same, this might help us to check the pilot plant results to reduce the range of the variable design variables and therefore develop bioprocesses and therefore get closer to attaining the goal set. And in closing, I'm certain that we all know that developing bioprocesses is tough, but mathematical models can actually make it easier. In the case of the carboxylate biorefinery, it's quite flexible to turn waste into energy. Models can help us in improving selectivity in this case, while providing us better understanding and narrowing down the operational space, but experimental work will be required to the relevant variables and also in developing processes. I would like to once again thank you for having me, and also for the financing provided to the Conserval and Ecoval projects. Marta Carvalho is the person responsible for this line of research in my research team. But then Juan Lemo, Ricardo, Alberto, and Juan Iglesias are other team members, and they all work very actively in this area in order to obtain these results. So thank you very much. Thank you, Miguel, for your presentation. Please stop sharing your screen if you could be so kind. So now we can give the floor to the very last panelist, Antón Taboada. I'm going to share your first slide. He is the project manager at Cetaqua. He will speak about end products recovery and purification. Good afternoon.
Good afternoon. You can start sharing your screen. Okay. I think it's ready. You can see it, right?
Yes.
Okay. So I would like to start by thanking FEUGA for organizing this event and for having us here and inviting us to participate. And I hope from now on we can see each other and stop all these virtual activities. Well, my presentation is going to be an addition to the presentation by Álvaro and Miguel. We are quite focused on this second part, on the research lines to produce volatile fatty acids. Miguel already explained the significance of metabolic models to stop the natural process of anaerobic digestion aimed at turning complex organic substrata into biogas, methane and CO2 through the different stages of the process. But not just that, also preventing, according to these parameters and aspects that he already mentioned, address the production according to the physicochemical properties of the substrata towards certain objectives. We have as goals to continue with these models in order to implement them into other types of waste and real waste, such as sludge, urban bio-waste, the canning industry waste, that have different types of organic compounds. So we were focused on how to produce fatty acids, selectivity, productivity, etc. But I'm going to focus now on what happens from that point. What happens once that those fatty acids are produced and fermented? There is a significant difference with the conventional process of anaerobic digestion. It is a process with 3 stages: solid, liquid and gas, and we achieve a in situ separation of the product. Once the organic substratum have been turned into biogas, this biogas is separated from the medium where it is produced. For example, in a water treatment plant, this is used to generate electric or thermal power for the needs of the water treatment plant. Then the solid or semi-liquid part of the digestion can be dehydrated. The liquid one goes to the plant, and the solid one is used for agricultural purposes like fertilizers. So the entire process is used. And when the objective is the production of VFAs, we need to add something, because that separation in situ without applying any types of energy for this separation, there is a different nuance, and this separation can be complicated because we are talking about a fermentation of sludge or bio-waste where we have a concentration of acids of 5, 6, 7, 8, 9, up to 10%. So in 1 ton of that output from the fermentator, we can get still 900 grams of water. Separating that water is not easy. So to give you an example, maybe you like cycling when you are going up the mountain and you look back and you say, okay, the things that the part that I already covered looks easier, but controlling the fermentation and stopping these reactions on the acids in order not to reach methanum could be the easier part of the process for different reasons. For instance, because we are already there, so what we have already done looks easier. But I'm going to be quick. I don't want to bore you with technical details. But the first difference with a biogas system could be that the dehydration of the sludge or bio-waste can be a la carte. So I'm going to explain myself. We get a solid stage with the waste that was not transformed, with the biomass that transformed it, and a liquid part with these VFAs and other types of compounds. How do we achieve this separation to get a solid and liquid stages? By adding chemical products such as surfactants or flocculants that interact with the negative parts that surround the sludge. So the sludge comes together and it separates from the rest. But the chemical products usually used on sludge management, for example, not only put together this solid part, but also due to this electrostatic neutralization, they also take part of the soluble compounds. So what we found is that conventional chemical products take with them those acids to the solid part, and therefore generating acids. And then if we can't separate them on the first stage, it makes no sense. So there are, luckily, there are other compounds more specific that it is truth that the precipitation of these acids is not prevented 100%, but we can reach 85%, 90% of separation on liquid mediums. So we are talking about a concentration of acids at not more than 10%, and the final users like Repsol, for example, as Carolina was explaining, showing interest on new products, the quality criteria need to be with a purity of more than 95%. So we need to add stages to concentrate and purify these acids. And I think that the technological development here is a little bit slow. Then in the fermentation stage, we know that if we do a series of things with some parameters, we get fatty acids. Sometimes we don't know why, but we have other technical alternatives. One of them would be the application of a micro, ultra, nano, and inverse osmosis meshes to eliminate some compounds like suspended solids that were not eliminated during the precipitation stage, ultra and nano filtration for smaller compounds to be separated from the acids, and then a inverse osmosis process to withdraw the water from the system. This technological trend is being promoted, but the results right now show that we cannot reach the necessary concentrations to market this dissolution of volatile fatty acids. within the Conserval project, we are focusing on the adsorption and desorption. The liquid and fermentation is in contact with a surface that, given the characteristics, chemical and physical characteristics, keeps or retains these VFAs, and the rest of compounds are left. I mean, they can go through it. Once this surface is saturated, depending on the surface, with these solutions, ethanol, these acids are separated and recovered. And then a third example that we are promoting within the Ecoval and Conserval projects, we have the extraction liquid distillation. An example for less technical people here would be when we mix water and oil. They are not mixed, they are separated on two phases. So this technology has a extraction part where we use a organic solvent that takes with it the volatile fatty acids to this organic stage, which could be the oil, and we obtain a product that is not interesting, which would be the water that was with the VFAs. But then we need to separate this organic solvent that has the acids from the acids. So a distillation column takes place, and there is an additional advantage here, because once the fatty acids have been separated from the solvent, this solvent goes back to the extraction column. This is the only way of having a feasible and economically viable system, because the solvent used, if it cannot be reused, it could be more expensive than the acids produced. It seems complicated in the short term that we will be able to separate individually the different acids produced, but and we are quite optimistic about it. We can get a product with concentrated acids, but this proportion of acids in the final product will be the proportion obtained in fermentation also. So I would like to stress the importance of metabolical and mathematic models to focus the fermentation towards a specific process depending on the market needs, business models that you have. So this would be my presentation. I just wanted to give you an idea. I think the technological development has always been focused on fermentation especially, but there are other borders, technical borders that we need to overcome in order to market these products. Thank you very much for your attention.